Hello, everybody. It is a big pleasure to me to open our seminar today. We have a talk by Gabriele Veneziano. He will tell us about the, maybe better to I tell you the precise title, from Newtonian to ultra-relativistic gravitational scattering, a third post-Minkowskian order. Okay, please. 1 hour.
Thank you very much. Thank you for the kind invitation to present this work. It's a little bit technical, the work, so I don't expect, that you will follow the fine details. And actually, I will try just to give the general physical ideas and, as few details as possible. Now, this is based on recent work with Paolo Di Vecchia, Carlo Heisenberg, Rodolfo Russo, and then there is some earlier work with Andrei Gruzinov, Ciafaloni, Colferai, and Kuradeschi. Now, okay, if I can scroll, that would be good. Okay. So as a way to introduce the subject, let me tell you, I'm sure you know, that the recent detection of gravitational waves from LIGO and Virgo has also stimulated a lot of theoretical work on the subject. Now, the traditional methods for computing, say, the expected waveforms from coalescing binaries and then interpret the signals are typically numerical relativity, post-Newtonian expansion, namely expansion around small velocities, the effective one-body approach of Bonanno-Damour, and these are entirely classical methods. Now, however, new approaches based on taking the classical limit of quantum mechanical scattering amplitudes has also been pursued recently. And since this series of talks is about quantum, I want to stress that this is an approach which starts at the quantum level and then goes to towards the classical limit. Now, this fact brought together two theory communities, one from classical general relativity and the other one from high energy particle physics. And this, I think, was very good. It generated a lot of synergy. For instance, we had a nice workshop in Florence, a virtual one, unfortunately, this year, and it was extremely fruitful. And actually, the high energy community has been interested in the gravitational two-body problem since long ago, since the late 80s. For instance, in 1987, as I will remember, there were parallel papers by Gerhard Toft, Amati Ciafaloni and myself, Muzinich and Soldate, and then followed by several other papers. Although they were done for completely different reasons, motivations, which I will explain below. Now, in that context of elementary particle collisions, it is necessary to go to very high, even trans-Planckian energies if you want to make gravity relevant. Otherwise, gravitational interactions for elementary particles are very small. So you have to go to fantastically high energies and to have to go even trans-Planckian if you want gravity to dominate. So the ultra-relativistic limit is absolutely needed. And it's also important to go to these very high energies in order to justify the existence of a semi-classical limit. Now, of course, what we missed completely in those times is that even massive astrophysical black holes can be thought of as elementary particles. This is basically because of the no-hair theorem. So the black hole is characterized just by its mass and spin, well, provided you look enough far away from its horizon. So for, at least for large impact parameter conditions. If so, those Gedanken experiments that we were looking into in the 80s become all but Gedanken, okay? However, for black holes, of course, the non-relativistic, by the way, NR in this talk means non-relativistic and not numerical relativity, occasionally could be slightly relativistic, but certainly not the ultra-relativistic regime, is the most relevant one. So the question is, should we then just forget about that earlier work done in the 80s and subsequent years? And my answer is no. And in fact, more or less 4 years ago, Damour argued that a useful input for the effective one-body approach can be obtained precisely from the high-energy ultra-relativistic regime of gravitational scattering. And he gave even an example, which maybe I will recall in a moment. Now, that made sense a posteriori, this statement of Damour, because if so, then the post-Minkowskian expansion, the post-Minkowskian expansion in particle physics language is just the loop expansion, the expansion in powers of Newton's constant, could then be anchored to two limiting cases. You have, on one hand, the small velocity post-Newtonian expansion, and on the other hand, you have an ultra-relativistic limit, and somehow you may hope to interpolate between the two. Now, there was soon after an interesting result, but also a puzzle at 3 p.m. 3 p.m. means two loops, okay? So in those two papers, in 2019, there was an impressive calculation by these 6 gentlemen who are listed down in the transparency. And this led to the first complete, but as you will see, it's not quite complete. That's why I put marks, 3 p.m. result. And this was done for general relativity and for 2 massive spinless black holes, say, or scalar particles. This was checked to be consistent. Their result was checked to be consistent up to 5 pn, 5th post-Newtonian order in the velocity, again in quotation marks because of what I will explain later. Later was also extended to 6 pn. So it looked pretty consistent, yet it presented a severe puzzle. Because if you took the high energy or just the massless limit of the result of Bern et al., that result exhibited a logarithmic divergence in energy, a log S divergence, in contrast with a perfectly finite result that our group obtained in 1990, so several years earlier. And we should note in this respect that gravity is supposed to be free from massless singularities, also so-called collinear divergences, as pointed out already by Weinberg in '67. And now, as a result, quite some controversy and even a lot of confusion came up. Furthermore, a little bit later, both the massless limit of our 90 paper by the work of those people, the authors are again listed at the bottom of the slide, and the Bern et al. Log enhancement at large S over m square, again in a paper by 2020, both were double checked. They were claimed to be correct and even universal, namely independent of the particular process at hand or of the particular theory. For instance, you could add supersymmetry have supergravity instead of gravity, and yet they would hold just the same. So the prevailing attitude for a while, since there was this contradiction, was that the two limits, momentum transfer much smaller than the mass, both much smaller than the energy, or mass much smaller than the momentum transfer, both much smaller than the energy, were unrelated. Okay. Now, however, the solution of the puzzle turned out to be different and more interesting, because we will see that there is actually a smooth connection between the two. How? We will see. Now, so let me give you an outline. In the first part of the talk, I will recall very quickly of the massless gravitational iconal following our approach. In particular, I will stress the result of this 1990 paper, because that is relevant for the puzzle. And then I will come to the main topic, which is how do we sharpen first the puzzle and then solve it. And then we'll see that the solution goes via what is called radiation reaction, RR. And then I will illustrate two shortcuts to computing radiation reaction. One is from a linear response approach, and one is related to soft theorems. Then, if I have time, or in the whatever remaining time remains, I will mention work on gravitational radiation from massless particle collisions. And then I will conclude briefly on some new challenges when you go one loop higher, namely at 4 post-Minkowskian order. So the quick reminder of these 20 years of work by ACV. Now, as I said, the motivation at the time were very different from those that are now. They were purely theoretical. For instance, on one hand, we were interested in seeing the emergence of classical and quantum, and in particular string gravity, from some Gedanken experiments, which were performed in flat space-time. So the calculations were done in flat space-time, but you could see a metric emerge from the calculation of diagrams and their resummation. And a more ambitious goal was to understand whether we could see a solution to the famous information paradox. And of course, if you could check unitarity of the resulting S matrix, even when the process is expected to lead to black hole formation, then we would have resolved the information paradox. Now, while the first part was quite successful, as I will tell you, the second was not quite as successful. And I will also tell you about that. So the point was to consider string and in the limit point particle collision at Transplanckian energies. So for light strings, massless strings, and so on. Now I'll give you very, very few details. And if you are more interested in more details, there are, for instance, my Jesus lectures, which should be online from 10 years ago. Wow, time goes by. So this is just supposed to be a drawing of a possible diagram which intervenes at two loops where you have a collision of closed strings, for instance, two gravitons or two dilatons, and then you exchange gravitons, which are these green closed strings. You produce particles, both massless and massive particles, and so on and so forth. And believe it or not, in some approximation, you can not only compute this diagram at these Transplanckian energies, but even resum a whole series of diagrams. Now, what are the typical parameters that enter in such a process where there is an impact parameter of the collision, which is related to the total angular momentum and the energy. there is a radius, a gravitational radius or Schwarzschild radius associated with the center of mass energy, g square root of s. For the moment, I'm in d equal 4. Most of the talk will be in d equal 4. There is a string length parameter, and in principle, there is also a Planck length parameter, but in string theory, it's related to the string length by some coupling constant. So if you take a weakly coupled string theory, the Planck length is very small, and the effect, the truly Planck scale effects, are screened by the string, as you will see in a moment. So let me concentrate on the first three length scales. You can therefore form two relevant ratios, and this is why the phase diagram for the collision is a two-dimensional diagram. And different regimes emerge. So if you want to be sophisticated, you will find several regions and several regimes, but roughly they can be divided in three parts. The region number 1 in the diagram is what we can call the weak gravity regime, of very large impact parameters, small deflection angles. And there we can discuss several things, which I will illustrate in a moment. Then there is a string gravity regime in which the string length dominates over both the impact parameter and the Schwarzschild radius. And this is a very interesting regime because you can see there string effects. And it's even doable. That's an amazing thing. What is harder to do is the third regime, which we can call strong gravity, because that's where you expect, on the basis of classical criteria, to have gravitational collapse or the formation of black holes. Okay, part of the incoming energy will collapse into forming a black hole, and that's where you'd like to understand unitarity. But that's where our results are not as striking as in the other two. So let's start with the weak gravity. In the weak gravity regime, we could see several things. We could restore elastic unitarity via an iconal resummation in impact parameter. This cures a problem which is there at tree level. You see indeed an emerging shock wave metric and the associated gravitational deflection and time delay. And this is very much related to Gerhard's approach, who starts indeed from that shock wave metric. And then there is this extension of the result up toward the G cube, which I will explain in a moment. And then there are other interesting aspects I will go over very quickly. T-channel fractionation, which means that the hard scattering, a scattering process which a large momentum transfer is actually dominated by large distance physics. I can explain you why, but I better go on now. Then we can see the tidal excitation of the colliding strings. Strings being extended objects, they suffer from tidal effects. And in that regime, we can check explicitly that unitarity is preserved, although it is no longer elastic unitarity, but it's full inelastic unitarity. And then in those days, we had the first go at gravitational Bremsstrahlung, and an energy crisis came up. And this is what I will explain towards the end of the talk, if I have time. Then in the region number 2, string gravity, we had quite interesting results. String softening of quantum gravity, a small impact parameter, which solves, for instance, a causality problem pointed out by Maldacena and company. We reach a maximal classical deflection in this regime. And if we go beyond, we find agreement with the Gross-Mende-Oguri paper, which, by the way, goes back exactly to the same year as 1987. There is the emergence of an effective generalized uncertainty principle. which makes scales below the string length unobservable. And there is an analog in the S channel of fractionation, in the sense that the final state starts to be to consist of a lot of soft particles instead of a single heavy string. And we see the emergence of some precocious black hole-like behavior. Finally, 2 words about the strong gravity regime, in which we made some progress. We identified the semi-classical contributions as being associated with some connected tree diagrams. These tree diagrams, in principle, could be resummed by solving a rather complicated effective field theory due to Lipatov. We made a 2D truncation of that theory, and then we could do quite some work, but of course this is far from being a rigorous approximation. Nonetheless, we saw the emergence of critical points or critical surfaces in the parameter space, and they were in good quantitative agreement with general relativity collapse criteria, or even with some numerical relativity results. However, when we try to go beyond those critical surface inside the collapse region, we had problems with checking unitarity. And especially Ciafaloni and Colferai tried a lot to solve that problem, but I don't think they found a real solution to it. So at some point we switched to simpler problems, hoping to go back to this unitarity question someday. And the 2 problems we addressed were, one was turning from string-string collision to string-brain collisions, which is an easier problem because the brain is a very heavy system. And this took me some 5 years of work. And the other thing, which is more relevant for today, we turn to study better gravitational Bremsstrahlung because of that energy crisis that we had. And I will explain at the end the progress we made there. It's time to ask whether there are questions before I go to the second and main part of the talk.
Okay.
I don't hear questions. So I go on.
May I
Yes?
ask a question?
Sure.
Can you explain what you mean by string regime in gravity?
String, sorry? Regime.
You
string
said strong
regime.
gravity and string regime.
Oh, if you have the, okay. So string gravity regime means that you collide 2 strings which have typical sizes of order of the string length L sub s, but you collide them at energies which are not too large, so that the associated Schwarzschild radius associated with the center of mass energy is smaller than the size of the strings. So in that case, even classically, you don't expect to form black holes. You know, there are quite well-established criteria, classical criteria, giving sufficient conditions for forming black holes. And for instance, typically you need an impact parameter which is smaller than a certain fraction of the Schwarzschild radius. However, this is true for point-like particles, but you have extended objects, then those effectively increase the impact parameter. So the string gravity regime is this regime in which impact parameter and Schwarzschild radius are both small compared to. Now, of course, this is a regime which doesn't exist in the point particle limit. So if you have standard GR with point particle sources, the point-like sources, that regime is not there. And strong regime is the regime in which the impact parameter is very large, so is small or is of the same order as the Schwarzschild radius. So you start to have first very large deflection angles, then maybe the two particles start to inspiral, and finally they collapse into a black hole. Okay, I don't know if this explains.
Yeah, sure. Thank you very much. I understood what you mean.
Okay, so let's then move to the main topic, which is the massive iconal. Now we are in the massive case, black hole encounters and mergers. And we try to sharpen first and then to solve the 3 p.m. puzzle. And this is work done by the Vecchia et al. Collaborations. It's about a year and some ago. So first of all, some definitions, since I will use these symbols. Okay, the S matrix in impact parameter space, or you can think of it as angular momentum, is written in this exponential form, where delta is sometimes called the phase shift. Okay, and itself, this delta has an expansion in powers of g. But of course, since it's an exponentiated form, each term itself can be expanded in g. The interesting thing is the expansion of the exponent. Okay. Now, the following results were found up to this 1990 paper, and now I quote it just for d equal 4 GR massless case. So for instance, at 3 level, you see delta 0. 0 means the number of loops. The index n means the number of loop, which is also the power of g plus 1. Now, at classical level, you get gs log b square. Notice the 1 over h bar, which is needed in order to make delta 0 dimensionless. And this 1 over h bar is precisely, what is meant by being classical or semi-classical. Think about the WKB approximation. The interesting thing is that, for instance, if you go to one loop, so delta 1, that delta 1 has no 1 over h bar. You can see that that quantity g square s over b square is a pure number without h bar. So this is why the one loop in the massless case does not give any classical contribution on its own. And by the way, this was one of the things that Damour used as a check for his own EOB approach. However, if you go to 2 loops, you have to go to 2 loops to find something non-trivial, then ACV found a perfectly finite real part of delta 2. I should remind you that the derivative of the delta 2 with respect to the impact parameter n divided by e is the deflection angle. Okay, so if the real delta 2 is finite, the deflection angle is finite. So this is a finite correction to the deflection angle that you get from the 3 level. The 3 level, when you take the derivative of log b squared, you get a 1 over b. If you divide this by square root of s, you get g square root of s over b, and this is just r over b, and this is just Einstein's typical deflection angle, okay? Just to get you on the good page. On the other hand, if you look at the imaginary part of delta 2, is no longer 0. It's even logarithmically divergent and infrared divergence. But this is not unexpected because you have massless particle radiation and the usual infrared catastrophe. Okay. Now, to put these results of ACV on a more rigorous and general grounds, for instance, we'd like to work in the massive case with Q smaller than M, or with extensions of GR, we try to use general properties of the scattering amplitude. One is real analyticity. One is asymptotics in order to write down subtracted fixed T dispersion relations. Once you know analyticity and asymptotic behavior, you can write dispersion relations. Crossing symmetry in our case is simply a symmetry between S and U. Perturbative unitarity, because you can relate imaginary parts to unitarity cuts, and so on. From those, we get information on the high energy limit of a crucial quantity, which is the ratio of the real part to the imaginary part. This is in strict analogy with what is done in high energy soft hadronic physics. It was extremely popular when I was young in the 70s and has become popular again when people look at the forward LHC data, total cross sections, elastic cross section, and so on. Now, here comes the result. I mean, the derivation is a bit longish, and you have to look at the papers. If you have, at some point, an imaginary part of A, which goes like some power of energy S and some log of S to some power P, then those model-independent constraints allow you to express the asymptotic real part of delta in terms of delta 2, in terms of the imaginary part of delta 2 and of the lower order phase shifts, delta 0 and delta 1. And this is the very explicit formula that you get, which is asymptotic in energy. So what you see here is that it are several interesting things. If imaginary delta 2 goes like a log S, there is no problem because you have this divided by log S and the log S disappears from real delta 2. But if im delta 2 goes faster than log S, for instance, if P is bigger than 1, then you have a problem, at least with this term. And then there are other things. For instance, if this power P is not equal to 1, then the result for delta 2 depends also on imaginary delta 1. And I told you that delta 1 is a quantum piece, but you see, this we know very well by now, these quantum pieces can be forgotten when you work at that order. But if you look at higher order, since they interfere with quantum, with 1 over h bar pieces, you know, the product is classical. So they have to be kept until the end if you want to extract the semi-classical limit for delta 2. But this term is also non-universal. So it's very bad. And when you look at the Bern et al. Result, you see, surprisingly, that P is equal to 2 for Bern et al. And if P is equal to 2, then you understand very well why Bern et al. Have a divergent scattering angle at high energy. Okay, so following this analyticity plus crossing plus unitarity argument, you see that the problem lies in the bad asymptotic behavior of imaginary delta 2 in Bern et al. Now, I rewrote the. On the other hand, if P is equal to 1, as I said, then everything is fine and there is no dependence on delta 1. And okay, you still have some infrared divergence here, as I told you. The log S goes away, but remember there was also an infrared divergence. But luckily enough, that infrared divergence is cancelled by the other piece, and the final result comes out fine. Now, this whole argument, therefore, shows that there is a crucial role played by imaginary delta 2. And by unitarity, by perturbative unitarity, this in delta 2 is directly related to the inelastic 3-particle cut of the 2-loop amplitude. Okay, this you can prove very easily. So this is the diagram, okay? You have a 2 to 3 amplitude where K represents a graviton, whereas the blue lines are our massive particles. So what we had to do, it was already computed in 1990 for m equals 0. So we have redone the calculation of a generic value of Q, the momentum transfer in the reaction over M. And one has to put a little word of warning. This diagram is called the H diagram, both, I mean, I think we are responsible for this name, and this name has been also followed by Bern et al. But in ACV and in B et al., this does not mean exactly the same diagram. In our work, what appears both on the left and on the right is the full 2 to 3 amplitude, okay? So not only this topology, it's the full high energy limit of the 2 to 3 amplitude. Whereas in Bern, it really represents that topology because they have their own bookkeeping of the contributions. Now, it turns out that the full is less singular than the H diagram of Bern et al. There is a cancellation between the H topology and what I usually call the double boxes topologies. And in the end, this is how only a single log survives in the imaginary part. It comes from the rapidity integration, and then everything works fine. So this was our hint that something was going wrong with those diagrams. So we then computed not just the 3-particle cut, but the full amplitude. But since it was too complicated in GR, we did it in n=8 supergravity, introducing massive external states via some Kaluza-Klein mechanism and at arbitrary energy. And this is very technical. We used these sophisticated techniques which go under the name of integration by parts and differential equations. And crucially, we did include contributions in the loops from the so-called full soft region of momenta in the loop. That means, for those who know a little bit this language, potential plus radiation regions, whereas some in Bern et al., they had restricted themselves to what is called the potential region. So we found, as I was saying, that the sum of planar and non-planar ladders gives a subleading contribution, which is, however, the same order as the one coming from this H topology, and that does the job of canceling. But what is very crucial was this inclusion of the radiation region in the integration. So let me just give you the result for n=8 supergravity, because I think it's very simple and in a sense very nice and beautiful. Okay, so this is real delta 2. There is a prefactor. Sigma is by now a very standard notation, is basically the center of mass, the S Mandelstam S variable, however, made dimensionless by this 2m1, m2. And at high energy, of course, sigma goes like S over 2m1, m2. Okay, it's dimensionless. So 2m1, m2 sigma is just S up to some mass corrections. At high energy, it is S. So apart from this factor, which of course is okay, there is this famous cosh, arc cosh, because arc cosh of sigma for large sigma goes like log of sigma, and it is precisely this is the beast, is the bad guy in the Bern et al. Result. Why? Because the Bern et al. Result generalized to n=8 in this paper, Para Martinez, Ruf and Zheng, is just this term. You see, this term has this log S, there is nothing to do. However, the inclusion of this radiation region in the calculation of the loop adds these two new terms, one without the cosh. And if you look at this one without the cosh and you go to large sigma, this goes to 1, and this just reproduces ACV 90. The other term has the cosh, you see, but precisely cancels at large sigma the Bernoulli result. Because if you go again to sigma to infinity, this goes to 1 and this goes to -1. The result is that what is left over multiplying the cosh is subleading in energy. So if you take the massless limit, it goes away and you're left exactly with the ACV result. Now note that the new and old terms behave quite differently in the non-relativistic limit. This you can see, for instance, from comparing these two pieces. The non-relativistic limit means sigma goes to 1, which also means S equal m1 plus m2 squared, the threshold. That's the small velocity limit. In that limit, you see the behavior near sigma equal 1 is quite different in these two terms. You see, it's a bit more singular here, I guess, than here. Yeah, because of this power 5 half. However, at high energy instead, it's quite different. They are of the same order and they cancel. Now you can rephrase the whole thing in terms of the 3 p.m. scattering angle. There are some small subtleties, but basically you have to divide by differentiate the previous result by the impact parameter, and there you find again these various terms. The Bernoulli result is this B, the ACV result is this. This has the new pieces. And what I would like to emphasize is that from the point of view of the post-Newtonian expansion, the new terms are distinct from the old ones by being half-integer Pn. Half-integer Pn means odd powers of the velocity, whereas the integer Pn correspond to even powers of velocity. You know, the Pn series is typically v squared plus v4, v to the sixth. This term have odd powers, and since Damour knows these things upside down, when we presented this result at the Einstein Institute workshop in 2020, Damour immediately, during my talk, immediately grasped the physical meaning of what we had found, because he saw in the slide these odd powers of velocity, and these are not time reversal invariant and so on. And therefore, he immediately said in the discussion that our half-integer Pn terms meant that we had added to the conservative dynamics of Bernoulli the effect of radiation on the iconal phase or deflection angle, is the same thing. So we added the so-called radiation reaction. And in fact, this led very quickly to a result by Damour, and then a little bit later by our group, which means two shortcuts were found to obtain the radiation reaction. Because of course one wanted immediately to generalize this result from n equal 8 to pure GR, but the calculations of all the diagrams looked quite awful. I mean, it has been done by now, but at that time it looked quite daunting. So Damour found a very smart trick. In fact, just a couple of months after our paper, he derived the radiation reaction in GR. And how did he do it? Well, he used the previous result with Bini, which relates the radiation reaction to energy and angular momentum loss. Then he argued that if you work at 3 p.m., only angular momentum loss enters and not the energy loss. Why? Because he claimed that there is a contribution to the radiation angular momentum, which is over the g square, whereas the energy, radiated energy is over the G cube. So that's why he neglected the radiated energy. And then using this linear response formula with Bini, he got the 3 p.m. radiation reaction correction to the actual GR calculation of Bern et al. And he got the smooth deflection angle, no more logs, and he even recovered our ultra-relativistic limit. And this result by Damour has been confirmed by at least 2 different techniques. One I will explain in a moment. The other is a brute force full calculation in n equals 0 in GR. Yet, I think it raises another puzzle, at least for some of us. Now, what time is it? 10 to 6? Huh? Yeah, it's a little late.
I think you have approximately 15 minutes.
15 minutes. Okay, yeah, we started a bit late. So let me say very quickly why we were still puzzled by Damour's result, because you may find this quite interesting. So the question is, what is the true J radiated and what is the relevant J rad? Now, the question which I immediately asked myself, how can one radiate angular momentum, say, at some order in G squared, and not radiate at the same order in G also energy? I mean, if you think in terms of a quantum person, and you associate this radiation to the energy and angular momentum carried by the emitted gravitons, it looks very strange that you can emit J and not emit at the same time energy. So with Grisha Vilkovisky, we have been looking into this now for, I don't know, 9 months or something like this. And we were much helped by Abi Ashtekar. In fact, there is a paper by GV square, GV and GV. As Grisha says, it's like Johnson and Johnson. And this is still being written. Just today, I think we finally agreed on how to present our results. So hopefully now it will be written within a month or so. So I'll tell you very roughly the story. It is well known to experts in GR that the definition of angular momentum and of its laws is affected by ambiguities in GR. These are related to BMS transformations. For instance, the shear of the metric written in Bondi-Sachs form is affected by BMS transformation. And under some rather general asymptotic stationarity conditions which are satisfied by our problem, can even be gauged away, the initial shear. And this defines what people call a canonical Bondi frame. And if you are in this canonical Bondi frame, then the angular momentum of the system at a past time like infinity coincides with the ADM angular momentum, and the subsequent loss of J is not over the G cube, but it is over, it is not over the G square, but it is over the G cube, just like the loss of energy. So this, in a sense, solves the puzzle in the sense that there should be loss of J of the same order as loss of E. However, the result of Damour is correct. So what's going on? And we found that there is another Bondi frame that we called intrinsic or barycentric. We still are fighting on the right name, with the property that the light cones of this Bondi frame coincide asymptotically with those which originate from the world line of the center of mass of the system. And we believe that this is the reason why the Bini-Damour formula should be used with the J-rad computed in this intrinsic Bondi gauge and not in the canonical Bondi gauge. And in fact, when you look at J-rad in this intrinsic Bondi gauge, you find exactly the J-rad that Damour had. So this, in a sense, makes us happy, makes also Damour happy. His result is correct, but okay, the mystery of having too much radiated angular momentum, I think, has disappeared. Now, the other shortcut is due to our group, and it goes via soft theorems. You have seen the importance of analyticity and crossing in relating different quantities. In fact, it is useful, interesting to recast our 3pm result in n equal 8 supergravity in an explicitly real analytic and crossing symmetric form. I skip details, but just tell you that you find that the real delta 2 and imaginary delta 2 always appear in a very special combination in terms of a variable x, which is related to the variable sigma that I introduced earlier, in such a way that there is an infrared divergent imaginary term. There is a finite log, as usual. You know, there is a log accompanied 1 over epsilon, but there is also a pi due to analyticity. Somehow is a log which comes from this pi, okay? It's a pi that comes from this log. And this is what we are interested in, this radiation reaction contribution. So to make a long story short, this implies a new intriguing connection between the radiation reaction piece of the 3pm iconal phase, the real part, and a soft limit, a zero frequency limit, and that enormously simplifies, again, the calculation. And the relation is quite nice. It's written here. The radiation reaction part of real delta 2 is simply related about the limit epsilon goes to 0. There is an epsilon. So this diverges like 1 over epsilon. You have to pick up the infrared divergent part. But then with a very simple argument, you can relate that thing to the so-called zero frequency limit of the radiation spectrum. d omega, this is known from the 70s, has a finite omega goes to 0 limit. And if you can compute this, then you immediately have the radiation reaction. And this we checked, both in n equal 8, it gives back our result for the radiation reaction terms. And then it's interesting, sorry, not in n equal 8, this is GR, sorry. This is GR. So we use that connection in GR. It's more complicated, the calculation, but at the end, the result is very simple. On the other hand, we also checked this connection in n equal 8 supergravity, where now it's a bit tricky because in supergravity, you have a graviton, a dilaton, and also because of this Kaluza-Klein business, we also have two massless vectors and two scalars. So you have to put to compute the zero frequency limit for emitting all those guys. And when you sum up all these numbers, you reproduce the radiation reaction formula that I had in a previous slide. You see, you get it from the sum of all these terms, where F is this inverse cosh, and you know this result. You see, it's just the same combination up to an overall factor of the radiation reaction. So this all works fine. Now, the last thing I want to tell you about, and I see the time is going fast, that it's about waveforms and energy loss. Now, many groups are still working on this. There are some very interesting results on waveforms. I have a few slides with some long expressions. Now, however, I should stress that the straight or the G cube result for the total energy loss, radiated energy, which was first given in this paper by Herman Pari-Martinez, Ruf and Zeng, leads in the ultra-relativistic limit to a new energy crisis similar to the one found in ACV 07. And in this respect, I should also mention that both Peter Diaz and Kovacs and Thor, in their 1970 papers on gravitational Bremsstrahlung, they put words of warnings on the limit of validity of their results about gravitational Bremsstrahlung if you go to high energy. Now, in the case of ACV 07, a resummation on G was found to be necessary in order to cure this energy crisis. And as I said here, in the hopefully positive time left, I will briefly recall that not fully finished story. Is it positive or negative, the time left?
No, it's positive, yes, approximately
Slightly positive.
5 minutes.
Okay, because then this, on the other hand, this I will have to go quickly. Oh, this is a slide giving the full result by Herman et al. You see they have an explicit formula for the radiated energy at order G cube. And when you look at the formula, you look at the high energy limit, it goes like a scattering angle cube times square root of sigma. Well, nu is a ratio of masses, which itself is a little bit tricky, but say take equal masses and it's just a number. But still, for sigma goes to infinity, this will diverge if you keep the deflection angle fixed. Of course, the deflection angle is over the G. So you say, well, if I work in perturbation theory, that is the smallest quantity, and I don't want to take sigma to infinity. But physically, you would like to understand what happens at very high energy and fixed deflection angle. So I'll tell you what is known in the massless particle collision, where you start right away from massless particle. So this is the process I don't have. So this was the energy crisis that ACV 07 had. We found that the spectrum of gravitons emitted had a nice cutoff in momentum transfer, in transverse momentum, 1 over b, but only a milder cutoff in frequency or energy. R cube over, that means the cutoff is b squared over r cube. But remember that r over b is a small quantity because it's the deflection angle. So this is a small number, which means a large cutoff. And when you integrate this formula over both k and omega, you find that the energy emitted in gravitational waves is of order, is just of the same order as the incoming energy. That is not so bad if you are near the collapse situation, is actually what you expect, but this also happens if the scattering angle is very small, where certainly you don't expect to radiate fraction 1 of the incoming energy. So ideally, one may have hoped for a different result, in which here you get that the cutoff in omega is 1 over r, and not this huge number, b squared over r cubed. If you had this, then the integration over k and omega gives a very reasonable efficiency for gravitational energy emission, which is of order of the scattering angle square. Now, what we did in these papers in 14 and then later in 15, 18 was to resum a whole series of contributions and see what is the real cutoff in omega. And the result since I have very little time, I'll give you just the result. The result is a complicated but very explicit and formula you can put in a computer if you want, and it will produce results. In fact, we have nice pictures. But let me tell you what happens. Maybe even better in pictures. For instance, this is d omega. You see in units gs theta square. You see that, first of all, you recover the zero frequency limit very nicely, but then also you find a very interesting, what we call a Hawking knee, because the spectrum starts to decrease on this rather universal curve, if you normalize this way, like 1 over omega, above omega equal 1 over r. So this is omega r, log omega r equals 0. That means omega equal. So what happens is essentially what I was hoping for, a cutoff in omega over the 1 over r, except that it's not a very sharp cutoff, exponential, and so on. It's actually a bit too weak because it's 1 over omega. And you teach me that if you integrate over omega, 1 over omega, it doesn't converge, right? So we don't have as bad as a divergence as before, but we still have a logarithmic divergence. And however, we can see that our approximations break down at a rather large omega of order 1 over r times theta scattering to the -2. So our guess with Gruzinov was that this is the real efficiency at high energy for the massless particle collision. And okay, so this is what we have. We also have a little bump that we found at very small omega, but let me skip over that and move to the very last slide to say that there are new challenges which happen at 4 p.m. or 3-loop order. There is a partial result for the conservative part, namely, again, neglecting radiation reaction, has been published by Byrne et al. This year. Unfortunately, it exhibits the same shortcoming as the 3 p.m. conservative results. It's only worsened because not only the ultra-relativistic or zero mass limit is singular, it is even more singular, and even at finite energy, sigma, the result is infrared divergent. In fact, the coefficient of the infrared divergence is related, as expected, to the radiated energy at the previous order. So at 4 p.m., adding radiation reaction, which is called tail contribution in GR, is absolutely essential for recovering a finite result at any sigma, not just at large sigma. It's a hard problem. Many groups have been working on this now for many months. And but there are partial PN expanded results available, but not any full post-Newtonian result. Summarizing, we have seen that the inclusion of the full soft region allows for the iconal phase and the scattering angle, including radiation reaction terms, to be continuous function of the velocity, so that the Newtonian and the ultra-relativistic classical limits get smoothly connected. We have found the analyticity, an intriguing relation between radiation reaction terms and the order G cube zero frequency limit of d omega, which is controlled by soft theorems. This looks mathematically equivalent to Damour's previous connection between radiation reaction and radiated angular momentum, with those caveats that has to be computed in a special Bondi gauge. But the precise physical reason for the equivalence remains to be understood. Here I mumble just the word BMS, saying that BMS is relevant, as many people like Strominger have emphasized, for soft theorems on one hand, and was very relevant, the BMS transformation, for discussing the Damour radiated angular momentum, right? So maybe there is a connection, but certainly I haven't found exactly what it is. Now, taking care of radiation reaction becomes essential, even away from the ultra-relativistic limit from 3 loops on, and it is an important but yet challenging problem. And another poorly understood problem is the spectrum of d omega at large omega and the total energy loss. Now, I think that eventually one would like to construct a unitary S matrix in the sense, in the semi-classical approximation, from which one can extract all sorts of observables that have a classical limit, including dissipative effects, radiation, and reaction to radiation. And to this purpose, I think that the iconal phase should be promoted to an operator. You cannot live just with a C number phase with complex values, but an emission operator, which itself will be endowed with a PM or loop expansion. And that expansion may even need resummations in certain regime. And this is what we are looking into right now. Thank you.
Okay, thank you very much, Gabriele, for your very interesting, very instructive talk. So, question, please. I see a couple questions. Who were the first? Okay, Igor Valovich, your question, please.
Hello, Gabriele.
Hi.
Thank you for the great talk.
Thank you.
Please compare briefly your computations in string theory with analogous computations in quantum field theory. I mean,
Yes.
in quantum field theory, we have renormalization group method and Froissart bound.
Yes.
What is the biggest difference between quantum field theory results and your results?
Okay. String theory is not extremely relevant except if you go to that string regime. In both cases, what is important is not to satisfy the Froissart bound, because in both string theory and in quantum field theory, there are massless gravitons and then long-range force, and you cannot prove at all that the Froissart bound must be satisfied because there are long-range forces. On the other hand, what is sacred, we think, is partial wave unitarity. You see, in the Froissart bound, there are 2 ingredients that go into it. One is partial wave unitarity, so there is a unitarity bound on partial waves. And the second is the short-range interactions in strong interaction, the absence of massless particles, and that limits the number of partial waves that can contribute. And this second ingredient is not there for gravity. So, but at the very beginning, in fact, I mentioned it, there was indeed a problem of unitarity for partial wave, because if you take a 3-level amplitude in gravity, goes like the square of the energy, gs square, and divided by t, say, if you exchange a graviton. And when you transform this into partial waves, you find that the partial wave goes like gs log b square. In fact, it's in my, this is in one of my first slides. So I think it's worthwhile to stress this. Oh, wow. So many slides. Huh? The point is that this large object, I think it should be, where is it that where I write the S matrix instead in terms of B of delta. You see, the point is that this okay, oh, here. You see, delta 0 goes like GS. So if you expand this in power, the whole thing in powers of the Newton constant, at order G, you just get that the S matrix is 2i delta 0. So you get 1 plus 2i delta 0, which means that the T matrix is 2i delta 0. But that is the partial wave, and you see it explodes at high energy. Now, what the iconal does is it brings something large to the exponent. And once it is in the exponent, it's perfectly unitary. So you satisfy unitarity, but you don't satisfy the Fusser bound. I don't know if this answers.
Do you think we have to compare your results with non-renormalized quantum field theory?
Non-renormalizable, you mean?
Yeah.
Well,
I
I see your point. No, yeah, it is true that strictly speaking, you should work with a theory which makes sense also in the ultraviolet. And this is why we started with string theory, because then there is a nice ultraviolet cutoff. However, once you go through the calculation, you realize that the classical limit is insensitive to the ultraviolet, because the ultraviolet divergences give local terms. And local terms, say in Q, in the momentum transfer, once you go to impact parameter, become delta functions in B. So if you are in, if you are, so we are only interested in the non-analytic terms in Q, which can give a long range effect, a large B contribution. So although strictly speaking, you are right, one should start with the renormalizable theory, or even better, with a finite theory in the ultraviolet, it doesn't matter for the large distance physics. So, I mean, somehow, you know, I like to say that gravity is just the opposite of QCD, okay? It becomes very easy in the infrared, but very hard in the ultraviolet, and, you know, QCD is just the opposite.
Okay. Thank you.
Okay. The next question is come from Ricardo Gonza. Please, Ricardo.
Hi, Gabriele. Thanks. So nice.
Hi.
So I have actually two questions. So hopefully there is time. So the first question related to the angular momentum issue. Yes. I guess to me, what it means to bond frame is you basically have amplitudes with really zero energy gravitons. And there you get disconnected contributions, and you can get something in G square. And I guess these are related to the BMS transformations.
Yes, that is true, because this, the thing you remove by these BMS transformations are precisely things which do not depend on time. Yeah, in that case, they are delta-like. They are delta-like in frequency. So, yeah, I agree. Mathematically, this is what it is. On the other hand, if you really think of measuring this angular momentum radiated, I mean, I can hardly see how zero frequency gravitons can give any angular momentum.
Yeah, I think Abai wrote a paper about the fact that you cannot observe this, right? In some sense, it doesn't matter too much.
Okay. The important thing is that you can use them in the formalism of Damour and Bini Damour. This is the object you have to use. I must say that Grisha Vilkovitsky is quite convinced that this is so. I'm still not 100%, it is not 100% clear to me that this identification of this other Bondi frame really clearly shows that that this is what you have to do, that what Damour did is what one should do.
Yeah, also these people in the Worldline calculation got the same result using exactly these zero energy gravitons, I mean, with the Worldline formalism, like, I mean.
Yeah, but they don't talk about radiated angular momentum, as far as I know.
No, they did, actually. their paper on the waveform, like they did talk about that, I think.
They talk, but I don't know. Maybe I missed some paper. I have not seen a paper in which people say, okay, so this is the radiation.
No. It's not. Yeah, it's computed, but yeah.
It's computed in this limit of the
Yeah.
Moore, and then you show that it is exactly his expression and so on. But yeah, you see, that's the point. If you want to use this Bondi-Sachs formalism, you know what these news functions are. The news functions are perfectly well defined, but there is an initial shear, you see, that you can, in principle, change by BMS transformation. And it's hard to imagine that therefore it carries in itself a physical gauge invariant meaning, the shear itself, the initial shear, which doesn't depend on you. Whereas the news are the derivatives of that entry of the metric with respect to you. Those are physical, and everybody agrees. And those certainly, give the correct order in G. But the point is that if you have this extra initial shear, then the formula for the radiated angular momentum has a piece in which you have, I don't know, however you want to call it, F dot times F. That's how Damour gets his order G squared term, because it has F times F dot. In the energy, you have F dot square, and there is nothing you can do. If you order G cube. But if you have F dot times F, and you don't remove the initial F, then you get an order G squared term. Now, the mathematics is quite clear. I mean, what I would like to understand better is how...
it's definitely interesting, because it's not invariant under BMS super
transformation. So on the other hand, the final result of Damour is gauge invariant, because it's the deflection angle. So one would like really to understand somehow there is a gauge dependence in its definition of the angular momentum loss. On the other hand, there must be some gauge dependence in the in the linear response formula, and somehow the combination of the two is gauge invariant. That's all I can.
The second question is about the energy crisis.
Yes.
Some of these points have been pointed out also in the literature on strong field QED, where they can compute like an electron in a plane wave background. You can do calculation at arbitrary high order, even computed radiation. And it seems to me that they pointed out similar features, like the fact that you need the quantum radiation reaction in some sense to correct the unitarity at high energies.
I see. So I see. Thank you. I mean, if you send me some references, I will be glad to look into that.
I think it's complementary to what you have done, basically, on this. You're talking about quantum effects. Your work at Ciappelloni, right? So it's in that case, you.
Yes, it's true. But on the other hand, if I go to the approach with in my paper, I went so quickly over it.
No.
The approach with Gruzinov was entirely classical. There is no H bar. What I want to emphasize is this, that in this formula that we got, sorry, it's a bit complicated, but I only want to point out that the Newton constant is here in R, okay? Which is related to the scattering. So this formula is highly non-trivial in R, is already a resummation. So even classically, you seem to need to resum in G Newton if you want to cover the massless limit or the high energy limit. Now, I'm very curious to see how it works in QED, indeed, or in electrodynamics.
Yeah, I don't know if they have an exponential with that. That I don't know, but I know that they can do that exactly. So that's the point, that you can do calculation exactly in that regime.
Yeah, you see, look at this result. For instance, this ZFL, this zero frequency limit, I think is well understood, and Sen got it from his thing. We got it with Bianchi. We got it this way. So we really can swear about this one, but it has a log of theta in it. And you can find it using Weinberg, because Weinberg gives you that there is a log of T over S. And but when you transform into scattering angle, finally it gives a log of G. So that's, shows you that there is something even non-analytic in G in some cases.
Oh, okay.
So that's why in the end I was saying, yeah, it would be nice to write everything in terms of an iconal operator, but the iconal operator will have itself an expansion in G, and who knows, maybe not even an analytic expansion in G, I don't know. We are still thinking about it.
Sounds a bit weird, but I understand your point. Yeah.
Okay.
Okay, thank you. Thank you.
Thank you for the question.
More questions, please? Please raise hand. Maybe I will ask questions. And Gabriele, in some of your slides, you wrote, mentioned about n equal 8 supergravity,
Right.
from one point of view. But from another side, you answering to Igor questions, you said that renormalizability is not so important. So my question is, in what respect a supersymmetry is relevant to your considerations?
Okay.
Does supersymmetry simplify something for you?
Yeah, for us, it was really only a method. We did not use in any way the fact that supersymmetry can make the theory better in the ultraviolet. This we did not use. It was a different kind of simplification that, of course, if you work in components and so on, you find mysterious cancellations, but essentially that even for the classical limit, it seems that to have a supersymmetric structure simplifies the loop calculations. Perhaps one, let's see, what would be a good explanation for that? I'm trying to think. You see, for instance, there are all sorts of topologies which were shown to be irrelevant in n equal 8 or in some extended supersymmetry case, but which cannot be neglected in GR. So in a sense, you have some price to pay because you have more degrees of freedom, you have the dilaton, you have also the antisymmetric tensor. And for instance, the double copy techniques work best with supersymmetry. And then if you want to recover general relativity, you have to subtract the dilaton, subtract other things, and so on. So I'm not so much in the technique of the multi-loop calculations, but I understand, in particular from my collaborators, that that it's really a simplification, and I think has nothing to do with the ultraviolet, but you never know. Maybe there is some interesting UV IR connection, and which tells you that they also simplify in the infrared. Certainly, you see, when you look at my result, let's see, this time it doesn't scroll. You look at the result for, no, not this one, the previous result. Oh. Let me use this. Maybe it's easier to find. the right formula. I want to emphasize just one thing. You see that the result in n equal 8 is very simple. The result in GR, it's more complicated, but what I want to show you is that the opposite is true if you look at things from the point of view of this infrared effect. Well, the final result is simpler in n equal 8, but the calculation, okay, the calculation of the infrared, it's more complicated because in GR you only have to worry about the graviton, and you compute its spectrum, and then you get a radiation reaction. Now here I only wrote the final result, but if I had to go in the same detail as for GR, it would be many amplitudes. You have for each one to compute the radiated spectrum, take the zero frequency limit for each field, for the graviton, for the dilaton, and for the two vectors. And by the way, there is an interesting point that it is because of these extra vectors and scalars that the radiation reaction in n equal 8, in our version of n equal 8, starts at a lower Pn order than in GR. In GR, it starts at 2.5 Pn, and this is due to just the graviton. There is also a dilaton. We thought for some time that it was the dilaton who was responsible for starting at 1.5 Pn, but when we did the calculation, we found that it was these extra vectors and two extra scalars which have a more serious, a more relevant Pn expansion. And by the way, this may be also the reason why people like Damour did not think that it was radiation reaction that was responsible, because they didn't expect to happen at this low order. So I think, no, for us, n equal 8 is a simplification in there are cancellations even in the classical limit, even at a large distance or small momentum transfer that are typical of supergravity and not of GR. That's all.
Okay. Okay, thank you. More questions, please? We can wait.
On chat, no.
We can wait a few minutes.
I hope I can go back to the slides.
Just pray.
Oh, no, they are just, yeah, that's right.
Yes. Well, if you want to show your time.
There is somebody even writing in Italian. I will go back to those and answer separately.
Oh, okay.
Okay. Okay, then I think everything else is clear or completely obscure.
No, well, I guess maybe too technical.
Yeah. No, I mean, I said immediately it's a rather technical
But
kind of work, but I think I hope to have given maybe some people the idea that there is interesting things to be done in this area, because I think it is on one hand challenging from a theoretical point of view, but it's not just pure formal theory. It can really have interesting applications to actual problems. And this is thanks to this idea that, after all, black holes behave like elementary particles.
Gabriele, and may I ask also one more general questions. What do you think dealing with four-dimensional cases is very important for you? For example, what happens if you consider high-dimensional cases from your
No, I think
perspective?
no. I mean, sorry. Again, I limited myself to the equal four, but for instance, much of the work with Amati and Ciafaloni was done for general D. For instance, superstring theory, in which you compactify a subset of the dimensions on small circles, so that, say, all the Kaluza clients are heavy and you can forget them. And then you get formulae which basically hold in GR for any number of D. And for instance, delta zero, we have it explicit for, for any D. It's a very simple expression. It only diverges, by the way, in D equal 4. Well, we don't go below D equal 4 because then, gravity is a little tricky, even in D equals 3. But for higher D, there is no infrared problems. And by the way, the work of ACV in 07, we did it for D equal 4, just to be more physical, let's say. However, we had to pay a price. The price is infrared divergences. And in fact, one of the approximations we made in our calculations was to neglect one of the two polarizations of the graviton that gave infrared problems. So this is, again, a limitations we had because we chose to work in D equal 4. If we had been in D equal 6, then there would have been no problem. So, for instance, an interesting thing could be to try to redo what we tried to do in 07, but in higher D. And no, I see no obstacle. Actually, we have some formula which hold at any D, but we simply didn't go through. Maybe it would be easier to construct the S matrix in higher D. After all, if you could solve the information paradox in some D bigger than 4, it would be already wonderful. Yeah, no, D equal 4 is not particularly good. I mean, except that we live in it.
Do you expect that one of a D expansion can help you?
That's a good idea. Reminds me of some recent work by Maltasena, no?
Maybe, yes.
Yeah, he has a paper on
Yes,
the information,
on
black holes, and I think it's about the transition between strings and black holes at large D. He has a recent paper. Well, we haven't thought about it because okay, we started with superstrings, so we thought that D was actually 10, and then a subset of the. But as I said, since I don't think it's the full ultraviolet consistency of the theory that matters, is really to expose the infrared. Maybe one could think about doing a large D, and maybe things simplify. Yes, sure.
Okay, thank you. There are two more questions, please. Georgi Savidi.
Hello, thank you for interesting talk. And
Hi.
I want to ask some naive question, maybe. Suppose that there is some event, collision of black holes and so on, and there is a gravitational radiation at infinity. Are you interested to find the relation between the angular momentum and the energy of a radiation? That's some.
Okay. Well, you say, so take a real situation with black hole collision. Because, this is also an interesting point. I didn't mention that, of course, most of the work of physical interest has to do with the with the inspiraling problem, what they call the bound state problem or the elliptic problem, okay? Whereas particle theorists, prefer to think about the scattering case, okay, like I did. But now, in both cases, you can ask certainly about the question of energy versus angular momentum loss. That's what you're asking about.
Yes, that's what.
Yeah. Now, that would be an interesting point. Do people worry about this? I think they do worry. For instance, Ashtekar, whom I mentioned, and that's why we consulted with him, has written recent papers about I think it's about the EOB, but certainly concerns this question of angular momentum loss. So I have to look back into it, but
with Grisha Vilkovitsky, is that the question you have been asking, or I incorrect?
In a sense, yes. In a sense, yes, we are asking the question of what is the true angular momentum loss. And we think that the true angular momentum loss starts at order g cubed and not at order g squared. Now, and then we said, well, but how come that Damour got the right result by postulating that there is an order g squared angular momentum loss? And then we think, I mean, this was my answer to Gonzo, that he was using another gauge, another coordinate system, which we think may be the appropriate one for his way of describing the linear response, okay? But, if you read the paper of Damour, you see that he talks about this being some mechanical angular momentum. What is the true definition of angular momentum in GR? See, it's tricky. For the mass, we think we know, and it's pretty unambiguous. We have the ADM mass.
Oh, there was a conference in I think that in Stony Brook, where they discuss all possible definition of the mass in gravity. It was a conference. They think there is not so easy.
Yeah, no, but I think for the mass and the energy, you have this nice thing, which is you take the asymptotic metric, and then you have this mass, this mass function, which is one of the entries of the metric written in a certain coordinate system. And this is the famous work of Bondi and then Sachs. And there is this beautiful formula giving the rate of energy loss by gravitational radiation. And there nobody is disputing that at all. Now, go to the paper, one of the recent papers by Ashtekar, written with somebody else. It's really about the fact that, unlike for energy, for angular momentum, we don't have a unique definition, but then most general relativists seem to agree that the most physical definition is the one in which you remove the shear initially. And in that case, the flux of angular momentum, you compute it by integrating over the sphere at infinity this certain quantity, but which is bilinear, okay, has a term with a time derivative and a term without a time derivative. But the term without a time derivative, if you say it is 0 at u equal minus infinity, then its value at any finite u will be of order its derivative, right? If it is 0 initially, then at some later time is the integral of the derivative. And then it's inevitable that in that case, also the angular momentum loss will be over the g cubed. So, and I think that that's what several people argue is the right definition. So there is this little mystery, but general relativity people think they know how to solve this ambiguity by a further fixing of the gauge, because you see, BMS is simply the fact that you still have some freedom in completely fixing the boundary Sachs coordinates, and then you have to use this extra condition to fully fix it. However, if you do that, you don't get the Damour angular momentum law.
Thank you very much for your insight. Thank you. Thank you.
No problem.
Okay, the next question is a question from Victor Veneziano. Please, Victor, ask your question.
I have a question a little bit more general even than previous one of George Savidi. Could you kindly tell us in what situation this radioactive reaction works that we can expect to watch it?
Yeah.
Yes, for instance, two black holes are moving around each other. So in what situation it can be watched experimentally?
Yeah, no, I think this is a good question, and thank you for asking it, because I thought perhaps it was clear, but it's very good that I say it well. The point is that when Bern et al. Do their conservative calculation, they don't quite get the physical scattering angle, deflection angle. They get some input to the EOB, effective one-body potential of Bonanno-Damour. Then what do Bonanno-Damour do with their effective potential? Well, first of all, they compute the orbits, okay? How in this effective potential, the two black holes orbit around each other. But then they do have to put at some point the fact that there is radiation, and therefore the orbits are not conservative, okay? You emit radiation, for instance, we know that the two black holes eventually coalesce. So how do they coalesce? Because they lose energy, right? If it was a non-dissipative process, they would keep orbiting each other forever. But they lose energy by radiation, and then they lose. When they lose energy, you can very easily imagine that their bending changes a little bit, right? The orbits bend. And this is, by the way, also the idea of Damour's calculation of the radiation reaction. He says, well, if you lose angular momentum, then consequently, also the orbits change a little bit. And this increases a bit the deflection angle. If I remember correctly, it leads to an increase in the deflection angle. So what I want to stress, answering your question, is that it is the deflection angle, including the radiation reaction, which is what you would measure if you had a scattering experiment instead of a coalescing. Otherwise, it's more complicated, the bound state problem. Then it's a question of precession and things like this. But suppose you are in a situation in which the two black holes pass each other at a large distance, and so they simply defect by, I don't know, 10 degrees. Well, it is 10 degrees, or is it, 12 degrees? It may depend if you include the radiation or not. And what we are saying is that the physical answer is the one which includes everything. So, in a sense, if you work with a conservative calculation, namely you include only the potential region in the integration, then you get a conservative Hamiltonian, which conserves the energy, conserves the angular momentum. but you don't get the full effect, which you have to add it separately. What we are saying is that if you're a particle physicist and you say, well, I include whatever the calculation gives me, you automatically include this effect. So this is perhaps another example of how, you know, people from particle physics can bring some new idea to the game, or some new techniques which include everything. So that is my hope, not to have to break down the calculation into two pieces, one with a conservative part and then add separately the radiative part. By the way, this restriction to the potential region means that, you know, you take only momenta, internal momenta in which some spatial components are larger than some time components and so on. And that approximation breaks even Lorentz invariance. So now, as a high energy physicist, I'm accustomed to keep Lorentz invariance all the time. And if you do that, then you have no choice. You have to include the full soft region, and you will get radiation reaction automatically. But that gives the physical measurable, you know, if you could be there and measure the deflection.
Yes, physical, but for instance, if we have Kepler problem, then there is no any radiative reaction, yes? And but
it's very small.
Very small.
It's not that there is not, but with black holes passing to each other at small distances compared to the Schwarzschild radius, then there is.
No, Gabriele, I want to realize when you include, for instance, relativity, then it is more chance to give this radiative reaction.
Exactly. In fact, it's an effect. So at lowest order, in the PN expansion, which is the expansion in V over C, there is no radiation reaction. The radiation reaction starts at some order in V over C. So that's why it's very small for our motion around the sun, for instance. But the point is that in this black hole physics, sometimes you reach V over C, which can be, I don't know, order 0.3 or, you know, something like this. So, and if you have our high energy Gedanken experiment with Transplanckian energies, and then you cannot neglect this radiation reaction. So now,
very interesting, Gabriele. You say that even in Kepler problem there is a radiative reaction. Yes.
Yes.
Where do you get it from?
Oh, no. I mean, if you consider, you know, there is some radiation. Okay, if you take the quadruple formula, I'm pretty sure that even our motion around the sun emits some gravitational waves. They will be so tiny that practically you don't see any effect. Okay, maybe it's a secular effect which takes the age of the universe before you see something. So it's a question. It's a quantitative question, but qualitatively, every time you have a change, a quadruple change, you emit gravitational waves. This is Einstein's formula.
Actually, there was an article of Einstein about gravitational radiation,
yes.
Where he said the following: if you take the hydrogen atom and the electron, quantum mechanics saves the stability, but now because of the gravitational radiation, it's again become unstable.
Oh, I did not know that. I see. I didn't know. He wrote a paper on this. He wrote
I think that is where he was find that there is a gravitational waves, at the end of the article, he posed this question.
Well, it's a good question, but I mean, I don't know. I don't know if it's correct, the conclusion, because certainly you could say, well, why don't you emit electromagnetic waves? We know because if you are in the ground state, you don't, right? There is no phase space for emitting photons. So I don't know, maybe.
No, gravitons. Now he say, why you cannot radiate gravitons?
For the same reason, if you are in the ground state, you have no energy to emit any graviton. But you have to do it quantum mechanically. I think in a classical model for the atom, you would emit gravitons as well. Gravitational waves, not gravity.
And I remember it very well, and I don't know. Yeah.
Yeah, it's an interesting question. Yeah, well, what happens to? Yeah, there too. I mean, certainly, if you have in any collision of particles, you would also emit some gravitational waves. In an experiment at LHC, you will. But the point is that the experiments at LHC, they are not at Planckian energies, right? If you could go to Planckian energies, then you'd see also emission of gravitational waves at LHC. But so that's why there were Gedanken experiments, thought experiments at the time, which were only for theoretical. But now with these black holes, they have become interesting physically.
Okay. More questions, please? If not, let's thank Gabriele for his great talk.
Thank you. Thank you for
Very
listening.
interesting discussion. Thank you, everybody.
Thank you.
Okay.
See you soon.
Thank you.
Thank you. Thank you.
Thank you very much.
Thank you very much.